More memory available to the graphics card than a 5090 or even the RTX Pro 6000. 128 gigabytes of unified memory on one chip. Still, to this day, the most powerful x86 APU you can buy. And 4 of them on one desk should basically be an AI supercomputer in your living room. Well, it took me over 3 months to get these things actually to work together in a cluster as fast as they finally did. And most of that was just me being wrong about what the problem even was in the first place. Let me back up here. The chip is the AMD Ryzen AI Max Plus 395, aka Strix Halo. If you watch this channel, you've seen me try this chip on mini PCs and laptops from GMK Tech, B-Link, Framework, Asus, and this one is the Minisforum MS-S1 Max. It might be my favorite. Well, all except one thing, and I'll get into that in a bit. And before this video is over, I'm gonna try to beat Minisforum's own marketing video on a cluster of these things. 4 boxes, 128 gigs of unified memory in each, half a terabyte total. Now that memory is shared between the CPU and the GPU, which you can configure in the BIOS. Out of the 128 gigs, the GPU can grab about 115 per box. Now the MS-S1 Max has a full PCIe slot, so I dropped a network card with a QSFP port into each one to network them hopefully in a faster way. All 4 cables go into a MikroTik CRS812 switch, specifically one 400 gig QSFP double D port. Double D means double density. 1 fat port, 4 machines. And if you do the math, that's roughly 460 gigs of GPU memory across the 4 boxes. Enough to run models the size of GPT-4 locally right here on my desk, in theory. For my Framework desktop cluster, I was using Llama CPP in RPC mode. It worked, but it didn't really actually scale very well. So this time, I wanted to try something new, a thing called Mesh LLM. The GitHub repo looked pretty cool. It's supposed to pool a bunch of GPUs into one OpenAI compatible API. Sounds perfect for 4 nodes. It did take some flag fighting to get one node going though. I got Qwen 3 8B working on it at 48 tokens per second, and this was using Vulkan. Then I tried to actually cluster it. I ran into all kinds of issues, networking, IP conflicts, all the usual stuff that make it hard to network all 4 of these machines. Finally, I got all 4 meshed together with a 4 millisecond ping. But the multi-node inference itself, 235 billion parameter MOE crashed, and Llama 3.1405B can't even see the GPU. So Mesh LLM wasn't going to be the answer for me, at least not in this stack. It was time to move on. This guy, Donato Capitella, has been doing Strix Halo cluster work too. You should check out his channel and his GitHub too. And on his GitHub, he ships these AMD Strix Halo toolboxes. Basically, Llama CPP prepackaged with ROCm and Vulkan for this specific chip. Really easy to set up. So I pulled down the images, spun up the containers, and these came with Ubuntu initially. So I pulled it down through DistroBox and ran it. Think of DistroBox as like Docker basically. It worked the first try. Then I threw Llama 3.1405B, Q2 by the way, the small quantization because this thing is huge. I threw it across 2 nodes via Llama CPP RPC, and it ran. I got 1.2 tokens per second. I know. Hang on, we're getting there. So technically it was a win. It was unbearably slow, so unusable. And here's the thing I really didn't get at the time. Llama CPP RPC is what's called pipeline parallelism. It lets you fit a giant model across your cluster, but it doesn't actually speed things up. Each token still has to walk through every machine in sequence. More machines means more steps before you get a token out. For years, this is how everyone was doing multi-node inference. Jeff Geerling's videos, Donato's early videos, and my own first Strix Halo cluster video too. All of us hitting the same wall with Llama CPP over RPC. What we wanted out of a cluster was 2 things: fit bigger models that any single box could hold, and get faster as we added more machines. Llama CPP RPC only did the first part. Bigger models, yes. Faster? No. What we actually needed was something different. Tensor parallelism. Instead of each machine handling a chunk of layers and passing the token forward, tensor parallelism splits every layer across every machine. So all the boxes work on the same token at the same time. More machines, more parallel compute per token. Actual speed up. Here on the left, I've got Llama CPP with RPC. As you can see, more nodes, the line stays the same. On the right, we've got tensor parallelism. More nodes, the line climbs. This is what we want to see. In the Python LLM world, tensor parallelism basically means VLLM. So that's the framework that I went with. But getting it to actually do tensor parallelism effectively across machines was its own adventure. See, VLLM works really well with NVIDIA GPUs. And to get it working with other GPUs, you kind of have to wrestle with it a little bit. Look, I've been trying to make this work for months, and I had the wrong idea the whole time. So these days, I'm always flipping between models. GPT for research, Claude for coding, Nano Banana for image generation, VO, Kling, and Runway for video, 6 tabs, 6 bills, and counting. Enter Chat LLM Teams. One dashboard houses every top LLM, and Route LLM picks the right one. GPT Mini for ultra-fast answers, Claude Sonnet for coding, Gemini Pro for massive context. They recently added Gemini 3 and GPT 5.1 the moment they dropped. Create professional presentations with graphs, charts, and deep research detailed content. Need human-sounding copy? Humanize rewrites text to defeat AI detectors. Need visuals? Pick frontier or open source models. Nano Banana, Midjourney, Flux for images, Magnific for upscaling, plus VO, WAN, and Sora for video, all built in. You also get Abacus AI Deep Agent to pretty much do anything. Build full-stack apps, websites, reports with just text prompts, and deploy them on the spot. They have Abacus AI Desktop, which is the brand new coding editor and assistant that lets you vibe code and build production-ready apps. And the kicker? It's just $10 a month, less than one premium model. Head over to chatllm.abacus.ai or click the link below to level up with Chat LLM Teams. Here's what I was thinking, okay? The cluster is slow. The cluster talks over the network. Therefore, faster network means faster cluster. That was what I was thinking. So I went shopping. After watching Donato's videos, he bought these cards. These are Intel 810s, and they have 100 gig NICs using QSFP cables. I loaded them up into the Minisforums, into 2 of them, connected 2 machines together, ran iPerf. I got 0 improvements. Here's with just 2 nodes my initial testing. Llama 3.370B, Tensor Parallelism 2, so 2 nodes, over TCP, so regular networking communication stack, not RDMA yet. This is a hint of what's coming. At 1 gigabit, we're at 5 tokens per second, and as you can see, the faster I increased it, it did not really help the speed here. Every upgrade was supposed to be the breakthrough, and every time iPerf 3 confirmed the throughput jump, but the token rate never moved up. The bottleneck was not the bandwidth. This is where I was completely wrong. It was latency. Every generated token needs several round trips between the machines, and each round trip under TCP costs hundreds of microseconds. More bandwidth doesn't make the latency lower. So I bought a lot of networking gear for apparently nothing. And by the way, I didn't even mention that switch I bought, the A12 MikroTik, for this very reason. I later used it in my Spark cluster, so it came in handy after a while, but this is the initial reason I bought it. However, there's one purchase I did make in this whole fiasco that did end up paying off. Now, what tipped me off to the latency thing was that I watched Donato's video on his Strix Halo cluster. He was getting 40% more throughput than I was. His trick? RDMA, which is Remote Direct Memory Access. So instead of TCP, where you're using the whole compute stack, you're skipping all that. VLLM Tensor Parallelism too, instead of Llama CPP RPC. I know I'm throwing a lot of terms around and acronyms. Hang out with me and I'll explain everything. Here's why latency is the thing. With a typical networking card, your computers talk to each other over TCP. Every packet has to be processed by the sending CPU, sent across the wire, received by the other CPU, processed again, and then copied into memory. That processing adds time to every single piece of communication, so round-trip latency ends up in hundreds of microseconds. RDMA skips all of that. The network card writes directly into the remote machine's memory. No CPU in the path on either end. So effectively, round-trip drops from hundreds of microseconds to about 5 microseconds. That's 200 times faster per round trip. And this isn't a new trick, it's how Apple pulled off clustering Mac Studios 2 over Thunderbolt, which has RDMA built in. I covered that in my Mac Studio cluster videos. To get speed up out of a multi-machine LLM cluster, you need round trip latency down in the single-digit microsecond range. RDMA is how you get there. And then Donato created this repository with Strix Halo VLLM toolboxes. And with these toolboxes, we can finally do it on Strix Halo. Just one problem though. His toolboxes, they say they run on Ubuntu also, but they're really geared towards Fedora. So I tried them on Ubuntu first. Yeah, it didn't work. This was hours and hours and days of networking, troubleshooting. So I gave up and I just installed Fedora on all the machines. Fresh Fedora installation, everything just worked. Well, almost. The built-in Ethernet jacks on these boxes did not work at all. So I went hunting for a Linux driver for it, nothing. Only Windows drivers are available on the Minisforum downloads. Fine, so I used USB Ethernet adapters on each box. Moving on, we'll come back to that. Now, when I ran VLLM plus ROCm on Strix Halo, I got 15.5 tokens per second on Qwen 2.5 7B. You gotta start out with small models. Okay, that's how you always start with the clusters because otherwise there's, small models first. This was actually slower on a single node than Llama CPP with Vulkan was, weirdly, which gave me 48 tokens per second. But this was the foundation because this is the stack that lets us do tensor parallelism. Here it is running on one machine. So then I plugged in a second Fedora node with a matching Intel E810 card. So we're not doing RDMA yet. All right, here we go. It is a little bit louder in here, isn't it? Hey, there it goes. Oh, we are on two machines now. Really nice utilization of the GPU on machine 1 and machine 2, but this is still TCP. 180 watts of power being used on machines 1 and 2. 22.9 tokens per second with this Qwen 7B model, up from 15.5. Not bad. A cluster that actually makes things faster, finally. So, 2-node TCP works. Time to actually turn on RDMA. And my Intel E810 cards wouldn't connect. Some kind of GID index handshake thing. I don't know. Annoying though. So I swap a Mellanox 4 card into one of the nodes, leaving the Intel in the other. So yeah, I'll spare you all the details, but it turns out the Intel iWarp and Mellanox Rocky are different RDMA protocols. They can't talk to each other at all. And the mixed pair ends up running slower than a single node, 9.1 tokens per second. We were going backwards. The lesson learned here, use matched hardware or nothing. With the second Mellanox card in the other node, match pair this time, Rocky V2 over IPv4. First try failed, second try failed. Turns out you need memlock, unlimited, and security limits. Log out, log back in. Every time I do that, I hold my breath and cross my fingers. And I've figured out that some kind of process keeps the cards locked. So I need to reboot every time I try. And there it goes. We're getting pretty decent utilization here. 96% on node 1, 96 on node 2, up to 97. And we're getting pretty symmetric RX and TX, receive and transmit over RDMA. This is actually working. Does it look faster to you? It's making a lot of noise, I can tell you that much. You can probably hear that in the microphone. 25 tokens per second. Yes. Single node, 15.5. Two nodes over TCP, 22.9. Two nodes over RDMA, 25.6. Very nice. This is finally the moment right here that we've been waiting for. Now it's time to expand that cluster. So we got 65% improvement here over a single node and 12% over just TCP. That extra 12% is what 200 times lower latency buys you on a small model. So on bigger models, it's gonna matter way more. Now I scale to all 4 nodes. Ray plus VLLM, TP, tensor parallelism equals 4 over RDMA. But of course, more bugs first. Gotta deal with that. Do I look tired? I am kind of tired. These videos with the clusters are always really difficult. But I'll spare you all the gory details.
Basically, one node's network manager auto-assigned a /30 subnet instead of /24. Then Nickel picked a different GID.
Anyway, I'm gonna save you the... But here we go. 4 nodes are up. Let's see. It's working. 97% usage on all 4 machines, on all 4 GPUs. And VRAM usage is pretty low, up to 30%, 7% on machine 4. So it's not very equal distribution here. And this is, by the way, TCP. So we have a little bit of a regression here at this point. Still, 29 tokens per second over 4 nodes. Now, I did run this for you live right now, and that's what I got. But RDMA did work for me at one point on on all 4 of these using Qwen 2.57b, at which point I got 38.3 tokens per second across the 4 nodes. By the way, it's a dense model, and it's almost 2.5 times the single node throughput. Near linear scaling on the small dense model here. But check this out. Same chart. This is Qwen 3 30b that I ran also, 30b A3b. So it's a mixture of experts reasoning model. In this case, it barely scales from 34 tokens per second to 38 tokens per second, going from 1 node to 4. Still an improvement though, but not as much. Why? Because that only activates 3 billion parameters per token. Not enough compute per token to make tensor parallelism worth the collective overhead. That's the rule that matters most on this cluster. Active parameters, not total parameters. Remember what I said at the start? I wanted to beat the marketing video, run a giant model. In that marketing video, they ran DeepSeek R1, 671 billion parameters. I know it's not the newest and greatest DeepSeek, but one step at a time, one day at a time, okay? First, we need to find a quantization that actually works, and a 4-bit AWQ quant. AWQ means activation aware quantization. That one is about 365 gigabytes on disk. So it doesn't fit on 1 box. It doesn't fit on 2 boxes. It barely fits across all 4. And for tensor parallelism, you need a multiple or a power of 2 machines. So either 2 or 4 or 8 or 16. I downloaded the model, synced it to all the machines, launched the LLM serve with tensor parallel size of 4, AWQ, weights loaded cleanly, 74 shards, 11 minutes. Then, init device never returned. GPUs were sitting idle, no error, no crash, just silence. Great. My whole dream just came crashing down. Without a crash. So just sitting there in silence, actually. So at this point, I was like, okay, let's try some other things with the same architecture, DeepSeek. So I tried DeepSeek V2 Lite, only 16 billion parameters, small enough to run on 1 node. And it turns out the AWQ on MOE models was broken on this particular iGPU. There is a pull request to support this, but it hasn't been merged yet. So if you're trying MOE with AWQ on this machine, don't do it. Try a dense model instead. We know a big dense model. So I found Llama 405B, instruct AWQ, integer 4, 219 gigabytes. Perfect. No MOE, just dense weights. Downloaded it, launched it, same kind of hang. Tried a smaller one, Llama 3.370B AWQ, same hang. Tried it on 2 nodes. Hey, it worked. 5 tokens per second. Okay, so at this point, this was a tensor parallelism 4 specific bug, unrelated to MOE, but still yet a different problem. This points to a general overall software difficulty setting these things up. It's doable, it's possible, but there's some issues to work through. All right. New plan. If MOE plus AWQ is broken and MOE plus BF16 crashes the kernel too, what about MOE plus compressed tensor W4A16? Oh, by the way, that's a whole different kind of quantization. It's 4-bit weight-only quantization, so int 4, plus it maintains a 16-bit floating point activations. So W4 A16. So I tried it on Qwen 330b, the A3b instruct version, 30 billion total parameters, 3 billion active parameters, launched it on all 4 nodes with tensor parallelism, and it loaded. I got about 37, 38 tokens per second, ran it a few times, so rock solid. That is great news. That's a private GPT class AI I promised at the start. Not 671 billion parameters DeepSeek I was after, but still real useful numbers. So here's where I ended up so far. 5 models scale cleanly. 3 of them hang when tensor parallelism equals 4, and DeepSeek R1, the one I wanted most, that one failed 5 different ways. If I were a more reasonable person, this is where the video would end. After all, 38 tokens per second on a 30 billion parameter model is pretty decent. Pack it up and ship it, right? But it just kept bugging me. And then I saw that our friend Donato has been busy. He's kind of behind on his YouTube channel, but he's been very busy updating his toolboxes. And he had commits that looked like they were exactly aimed at my failures. He made a specific build for this iGPU, and every fix I needed was sitting there in a newer image. And there it was, right there in the repository. Fedora 43, which is what I installed, ships with kernel 6.17, but Donato, our friend here, was on 6.18, and the newer Rockham was compiled against kernel 6.18. So I updated my kernel to 6.19 and then did a reboot. Clean boot, ran it, no seg fault, 16 tokens per second, exactly the old baseline, so we're good with one machine. And then I went back and tested every single model again, the ones that were failing with the old kernel, and guess what? Where I had hangs before, now every single model was working. Even the newer ones too that were unsupported before, like Gemma 4 26B, now I got 30.5 tokens per second. Qwen 3.5 27B, almost 12 tokens per second. A big chunky dense model Llama 3.3 70B, it hung before it hanged, no. Whereas before it hung 6.3 tokens per second now. And the big chunky boy, still unusable, but at least it ran. Llama 405B, 1.25 tokens per second. Slow, sure, but running. And that left one model, the one that I wanted most from the very beginning. Back to DeepSeek R1, this time the W4A16 quant on the new stack, and you can hear it. You can hear it. After a clean reboot, all 4 nodes are running. Memory utilization is at 99% on all 4 machines, and it's running. It's actually printing everything out for me. Now this is actually 37 billion active parameters in DeepSeek R1, so this takes some serious compute time. Now you tell me, is this looking like it's faster than Minisforum's demo? We're using about 180 to 187 watts on every machine. And yeah, there's definitely a lot of heat coming out the back here. 4,058 tokens generated in 10 minutes. And guess what? Minisforum's own product video, same chip, same 4 nodes. DeepSeek R1 quantized to 4 bits. Their numbers, 5.94 tokens per second. Mine, with VLLM tensor parallelism, 6.23 tokens per second. Yes! It's about 5% faster than the vendor's own demo. Whew. On a fully open source stack. 13 models, 3 cluster sizes. The empty set means it didn't fit. Everything else ran fine. The fastest, Qwen 7B dense and Qwen 30B MOE at 38 tokens per second. The biggest, DeepSeek R1 671B at 6.23 tokens per second. One thing about why any of this works, AMD removed RICL from their builds, and that's the library Donato originally got into ROCm through his own pull requests. He had to patch it back in by hand to keep multi-node working. It's early. It'll improve, I hope. If you build this yourself, install kernel 6.19 first. Fedora 43 ships with 6.17. One last thing. At the start I said the MS-S1 Max is my favorite Strix Halo mini PC. All except one thing, and that's that Realtek NIC that just drops. Works fine on Windows. I tried it. They have great Windows support, but on Linux, kind of annoying. Otherwise, the hardware is great. So Minisforum wins on expansion. Framework wins on plug and play. Watch that framework cluster video right over here. Thanks for watching, and I'll see you next time.